right now, your smartphone is essentially blind.
Yeah, completely.
I mean, when you lift it up to unlock the screen, it doesn't actually see your face. It doesn't,
Yeah.
perceive a nose or eyes or a smile.
No, it's just math.
Exactly. It's performing millions of rapid-fire math equations on a dense grid of numbers.
Mm.
And we interact with computer vision every single day, right? From that phone in your hand to autonomous vehicle stopping at a crosswalk. And we just entirely take it for granted. So today, we are going to expose the illusion of sight. Welcome to this deep dive.
It really is a fascinating illusion to unpack because computers, obviously they lack biological eyes, there's no retina, no optic nerve, none of that.
Right.
But they emulate human visual perception through some truly incredible mathematical building blocks.
And that is our mission for you today. We've got a brilliant stack of source material for this. It's a comprehensive technical training module on computer vision concepts. And we are going to demystify the magic behind artificial intelligence's eyes.
We're taking you all the way from the absolute basic math of a single pixel straight through to advanced AI systems that can, well, basically hallucinate entirely new photorealistic images on command.
It's wild stuff.
It is. But to understand it, it requires stripping away everything you think you know about a photograph.
Right, like what is a photo actually?
Exactly. I mean, we all know digital images are fundamentally multidimensional arrays, right? Grids of RGB values ranging from 0 to 255. That's just basic computer science.
Red channel, a green channel, a blue channel, all stacked together to make millions of colors.
Yeah, but just having a spreadsheet of numbers doesn't mean the computer understands what the numbers represent.
Because a grid of pixels is just static data. I mean, I might know that cell A1 is dark blue and cell B2 is light blue, but how do we get the computer to actually notice things about that data, to process it and find a shape?
We use filters, or mathematically speaking, they are called kernels.
Kernels.
Yeah. Picture a tiny secondary grid, let's say just a 3x3 square of numbers, which act as weights. To process an image, you take this tiny 3x3 grid and you slide it, or convolve it, across the entire massive spreadsheet of the original image.
Just shifting it one pixel at a
Yeah,
time.
exactly.
Okay, I really want to visualize the math happening when those two grids overlap. So we're sliding this tiny 3x3 kernel over the giant image array. What is the actual calculation?
So you multiply the pixel values of the original image by the corresponding weight values in your tiny filter.
Okay.
Then you add all 9 of those results together. That single final sum becomes a brand new pixel value in a completely new array.
So you calculate that sum, slide the kernel one pixel to the right, do the math again, and just keep going.
You keep going until you've mapped out a transformed version of the entire image.
Okay, let's unpack this with the example from the source material because it uses something called a little place filter.
Right, a classic one.
Yeah, and in this specific 3x3 grid, the center number is a positive 8. But all the surrounding numbers in the grid are negative ones, and they apply this to a photo of a golden retriever holding a stick in its mouth.
The Laplace filter is essentially an edge detection mechanism.
And it totally transforms the photo. I mean, when you slide that specific arrangement of negative ones and an 8 over the spreadsheet of the golden retriever, all the flat, solid surfaces in the photo just turn pitch black.
Completely black.
But the boundaries between different objects, like the dog's fur against the grass or the hard edges of the wooden stick, they suddenly glow. The math literally turns the photo into this neon edge highlighted outline.
And that's entirely because of the way those weights are distributed. Think about the positive 8 surrounded by negative ones.
Right.
If you slide that over an area of the photo where all the pixels are the exact same color, say a clear blue sky, the positive and negative multiplications cancel each other out to 0.
And 0 is black.
Exactly. 0 is black. But when that kernel hits a boundary where the pixel values suddenly change, from dark dog fur to bright green grass, the math doesn't cancel out. It spikes.
Oh, wow. So it's literally designed to react strongly only where the numbers are changing rapidly.
Which naturally corresponds to the physical edges of shapes in the real world.
Right. But an edge is just a glowing line on a black background. How does the system cross the chasm from seeing a jagged line to actually understanding that the line belongs to a golden retriever? I mean, seeing an edge is one thing, but knowing what it belongs to is an entirely different problem.
Yeah, it requires a hierarchy of computer vision tasks, which, escalate in computational complexity.
The training module illustrates this by looking at a smart checkout system at a grocery store, right?
It does. A customer places a piece of produce on a scale, a camera looks down, and the store wants the AI to automatically identify the fruit and charge the right amount.
The absolute dream of never scrolling through that endless digital menu trying to find the specific barcode for a Fuji apple.
Exactly. So the most basic approach to solving this is image classification. The model takes the visual features of the entire image and predicts a single text label for the main subject. So the camera looks at the scale and just outputs apple.
That feels incredibly limiting, though. What if I'm ringing up a fruit salad? Like I've got an apple, an orange, and a banana all piled on the scale together.
Well, image classification completely fails there. You'd have to step up to object detection.
Okay, what does that do?
This model examines multiple regions of the image to find individual objects, returning the exact coordinates of rectangular bounding boxes around them. So it outputs a data set saying, here is a rectangular box in the bottom left containing an apple. Here's a box in the top right containing an orange.
Wait, a rectangular box around a curved banana is going to be incredibly sloppy.
Extremely slow.
There is going to be a ton of empty white space, or worse, overlapping pieces of the apple included inside the banana's bounding box. If the grocery store needs extreme precision, maybe they're estimating the exact volume of the fruit. A box isn't going to cut it. So how does the AI isolate the actual curve of the fruit?
Then it has to move to the most sophisticated approach, which is semantic segmentation.
Semantic segmentation.
Yeah. In this model, the AI abandons the bounding box entirely. It classifies every single individual pixel in the entire camera feed.
Every pixel.
Every single one. It decides pixel A is an apple, pixel B is an orange, pixel C is the metal scale. The result is a precise, pixel-perfect mask outlining the exact complex geometry of the banana.
That must require massive computational power.
It does.
And it brings up the core mechanism of all this. Because identifying those fruits with pixel-perfect precision requires a system that learns. We just talked about how filters manipulate pixels to find edges. But if I'm an AI, how do I know which mathematical filters to use to find the curve of an apple versus the jagged edge of a stick?
You use a convolutional neural network or a CNN.
CNN?
Right. If filters are the tools, the CNN is the system that learns which tools to select.
Okay, let's track the architecture of a CNN step by step, because I really want to understand how the learning actually happens here.
Sure. Step 1. You feed the network thousands of images with known labels, like label 0 is an apple, label 1 is a banana.
Got it. Answer key included.
Step 2. The images pass through layers of filters. But initially, the weights in those filters, the eights and negative ones we talked about earlier, are completely random.
Wait, really? So the AI is just throwing random math at the picture to see what shakes out?
That's exactly what it's doing. It generates arrays of numeric values called feature maps. Then the network pools those maps.
Pulls them.
Yeah, it scans them and downsizes them,
Right.
basically throwing away irrelevant data to emphasize only the most prominent visual features.
Okay.
Then step 3 is flattening. Those two-dimensional grids are unrolled into a single, massive, one-dimensional list of numbers.
Just a giant straight line of sequential data.
Precisely. Step 4. That flattened list is fed into a fully connected neural network. And finally, step 5. The output layer. The network uses a mathematical operation called a softmax function to output a probability distribution across the classes.
Okay, hold on. I want to pause on softmax because it sounds like serious jargon. What is it actually doing to that straight line of numbers?
Oh, the softmax function is beautiful.
Oh, yeah.
It really is. It takes the raw, unconstrained output scores from the neural network, which could be, any wild numbers like -50 or +4,000, and it applies an exponential function to them.
Okay.
Specifically, it raises Euler's number to the power of each raw score. This forces all the numbers to be positive. Then it normalizes them by dividing each exponential value by the sum of all the exponential values combined.
Whoa, okay. Dial it back a second. The math is elegant, I'm sure. But practically speaking, what is the result of doing all that division?
The result is that it forces all those wild numbers into a clean set of fractions that always, without fail, add up to exactly 1.0.
Ah, I see. So it turns raw, chaotic math into percentages.
Yes. It might output something like, I am 20% sure this is an apple, 50% sure it's a banana, and 30% sure it's an orange.
But because we fed it the answer key in step 1, we know it's actually an image of a banana.
Exactly.
So the banana probability should have been 100% and the others should be 0. This is where the gap between its guess and reality exists.
And that gap is called the loss. Calculating that loss is the entire foundation of machine learning.
The whole thing.
Yep. The model's singular goal in life is to reduce that loss to 0 using a process called backpropagation.
Let's visualize backpropagation for a second. It's less like a data funnel And it's more like an eye exam.
An eye exam.
Yeah, you're sitting in the chair, and the optometrist flips a lens and asks, is this clearer or blurrier?
Oh, I like that.
Right. The AI is constantly flipping its own lenses. It checks its 50% guess against the answer key, realizes it's blurry, and then mathematically reaches back through all its layers to tweak its own internal dials, those random filter weights.
The optometrist analogy works really well because it's an iterative feedback loop. The AI tweaks the weights, runs the image through again, checks the new loss, and asks better or worse.
Just constantly refining.
It does this over and over in cycles called epochs. It uses gradient descent to mathematically find the exact filter weights that extract the features of a banana with the lowest possible error.
That is brilliant. CNNs are incredible at learning visual features.
Mm.
But as we move into the second half of the source material, they kind of hit a massive wall, don't they?
They do.
Because what if we want the AI to do more than just draw a perfect pixel mask around a banana?
Mm.
What if we wanted to understand the context of a photograph and, say, describe it in complex human language?
Well, CNNs are fundamentally blind to semantic context. Identifying an object is a localized task. Interpreting the meaning of an entire scene requires a complete paradigm shift. Computer vision researchers realized they couldn't solve this with just pixels. They had to look at how AI processes human language.
They borrowed from natural language processing, specifically the transformer architecture.
Yes, transformers revolutionized language models. They take huge volumes of text and encode words, or tokens as they're called, as vector-based embeddings in a massive multidimensional mathematical space.
Think of this encoding process like building an invisible 3D map of human language. On this map, a token like the word hat and a token like the word head are going to be positioned very close to each other.
Exactly.
Not because they're spelled similarly, but because they share context. You wear a hat on your head. The AI is mapping relationships.
It creates a space where distance equals semantic similarity. So the breakthrough was asking, if we can map language based on context, can we use the exact same architecture to map images?
Which gives us the vision transformer.
Right. Instead of words, a vision transformer chops an image up into tiny square patches of pixels. It extracts those patches and turns them into vectors. Then it uses an incredibly complex mechanism called attention to figure out the contextual relationships between the patches.
So on this new visual map, the pixel patches that look like the brim of a hat end up living very close to the pixel patches that look like human hair.
Yes.
The model doesn't inherently know what a hat is. It just mathematically observes that these specific pixel patterns constantly hang out together in the training photos.
But here is where the true paradigm shift occurs. We have a map of language, and we have a map of visual features. If you train a model on data that includes both images and text descriptions, you can merge them.
And this creates a multimodal model.
Exactly.
Here's where it gets really interesting. The source material mentions cross-model attention as the way they merge.
Yeah.
How does that actually work? Like, how do you mathematically glue words to pixels?
Cross-attention acts like a sophisticated querying system between the two maps. Think of it as a massive matching game. The text acts as a query. It asks a question. The visual patches act as keys labels on the data.
A matching game. Got it.
The attention mechanism calculates the mathematical similarity between the text query and the visual keys. If a query for the word dog heavily matches the keys of a furry pixel patch, the model bonds them together.
So they basically lay the map of human language directly on top of the map of visual features,
Essentially, yes.
aligning the queries and keys until they lock into place in a single, unified, multi-dimensional space.
And this is what allows a model to look at an image it has never seen before, say a unique photo of a person eating an apple, and instantly generate the caption, "A person eating an apple."
Wow.
It extracts the visual features, searches the merged vector space, and pulls out the exact language tokens bonded to those features.
Which naturally invites a staggering question.
Hmm.
I mean, if the AI has this perfectly aligned, multi-dimensional space linking words to visual features, can it run the engine in reverse? Like, if it can look at a grid of pixels and output a sentence, can we give it a sentence and force it to synthesize the grid of pixels from scratch?
Reversing that flow is the foundation of modern image generation. If you can map the visual features linked to language, you can absolutely take a text prompt from a user and generate a brand new image.
But how does it actually construct the image? Where do the pixels come from if it's not just, copy-pasting existing photos from the internet?
Most state-of-the-art models use a process called diffusion, and it doesn't start with a blank white canvas. It starts with pure, random, static,
Static?
absolute pixel noise,
Like the black and white snow on a broken television set.
a completely chaotic grid. The model takes your text prompt, say, a dog carrying a stick, and finds those bonded features in the multidimensional space.
Okay.
Then it begins an iterative denoising process. Step by step, it evaluates the static and subtracts a tiny layer of noise, nudging the chaotic pixels slightly closer to the mathematical features of your prompt.
The training module actually shows a frame-by-frame breakdown of this diffusion process, and it is wild to look at.
It really is.
Frame 1 is just TV static. Frame 2 is slightly less static, but there's a vague, dark blob accumulating in the center.
Right.
Frame 3, the blob develops the rough geometry of an animal. It iterates again and again, stripping away the noise until the final frame is a crystal clear, photorealistic image of a golden retriever with a stick in its mouth.
It is a mathematical sculpting process. You are literally carving the image out of the noise.
That's crazy.
The model learned to predict what noise looks like, and by subtracting its prediction, structure emerges.
Think about how wild that is for a second. It's chiseling a dog out of pure static, using the gravitational pull of text embeddings.
And this framework is expanding rapidly. The source notes that this exact diffusion technique is already generating video.
Video, too.
Oh yeah. The model identifies the visual features associated with the prompt, but it also has to calculate temporal progression and physics. It has to denoise the static in a way that ensures the dog's legs move sequentially, and gravity behaves correctly across multiple frames. It's carving moving reality out of static.
We've covered a staggering amount of technical ground today. We started with flat arrays of RGB numbers from 0 to 255.
We did.
We watched Laplace kernels slide across those grids to calculate edges. We explored how a convolutional neural network acts like an optometrist, using backpropagation to constantly tweak its lenses and learn the difference between an apple and an orange.
Right.
And finally, we saw how transformers use cross-attention to fuse language and vision into a unified map, allowing diffusion models to literally sculpt reality out of noise. So what does this all mean for you?
Well, if we connect this to the bigger picture, it's easy to get lost in the complexity of softmax functions and vector embeddings. But the critical takeaway is how these abstract concepts shape the physical world.
Exactly.
The exact mathematical operations we just unpacked are what operate inside an autonomous vehicle, allowing it to instantly segment a live camera feed and safely brake at a crosswalk. It's everywhere.
It's the same underlying logic, allowing a grocery scale to instantly ring up your produce.
Yeah.
The abstraction becomes our daily reality.
It fundamentally changes how machines interact with our physical space. And that leaves us with a fascinating final thought to ponder. Based on that massive paradigm shift we explored with transformers,
Definitely.
if these advanced multimodal models are mapping visual features, the colors, the shapes, the textures, and human language into the exact same multidimensional mathematical space, does the AI essentially think in a hidden universal language of its own?
That is the question.
A language that isn't English and isn't purely visual data, but a completely alien geometric bridge between the two. Something to mull over until next time.